So the next critical thermodynamic property we're going to introduce is Gibbs free energy. Gibbs free energy has a certain definition, just like Helmholtz energy. Gibbs free energy exists for any process, but Gibbs free energy we're going to say is important for a process that's simultaneously isobaric and isothermal, because during those types of processes it maps onto the second law. Now, this is why you've heard about delta G or G giving us information about spontaneity, because for most chemical situations, we can make them isothermal by using like an isothermal bath, and most of them are run just open to the atmosphere, so things can be considered isobaric. So G is important for us because these are common situations that we find ourselves in as chemists. So if it maps onto the second law for these processes, but only for these things being simultaneous, right? Isobaric and isothermal simultaneously. If it maps on to the second law, then Gibbs free energy, which we call G, in particular delta G, right, is going to predict, or dG, is going to predict spontaneity. So there's nothing magical about G. There's nothing magical about A. It's just that they are ways to get at the second law. Right? The second law is the only thing that ever really predicts spontaneity. It's just sometimes these other functions that we create with our Legendre transformations, they can map onto the second law. So let's take a look at the definition of G, the mathematical definition, and let's do the mapping ourselves and understand where it's coming from. All right. So our definition of G looks like this. G is equal to H minus Ts. You'll find that on your thermodynamic handout, right? If we now apply a change to both sides, we're going to get a dG is dH minus Tds minus S dt. Okay. Now let's apply some keywords. We're going to do isothermal and isobaric. And those are simultaneous keywords. We know that for a situation where we have an isothermal process, our dTs are going to go to 0. Just like our derivation of Helmholtz energy and mapping it onto the second law, what we're going to do next is we're going to divide by T, because it doesn't look like we can really use our other keyword directly yet. So let's divide by T. So I'm going to be left with dG over T. Looks like dH over T minus ds. Oh, okay, this should be a little bit familiar. I'm running into a situation again where it looks like I have components for the second law. I see that I have a ds. I know that when I deal with the second law, there's a positive in front of this ds, so I'm going to bring a negative through to each term. Okay, so this right here, we know, without a subscript, is ds for the system. Okay, it's being added, that's good. Okay, so now let's make arguments that this is ds for the surroundings. Okay, that involves using this keyword and remembering how we take ds for the surroundings, how we usually calculate it. What we have to find is Q for the system, take the negative of it, and divide by temperature. Well, hold on a second. For an isobaric process, dH is Q. Okay. So just like for the Helmholtz process where we prove that this term deals with the heat of the system, opposite in sign because it's going in the surroundings, divided by the temperature of everything because everything's isothermal, so that is T of the surroundings, this right here, this term becomes ds for the surroundings. Okay, I'll just write this here. dH equals Q for an isobaric situation, right? So then this right here, this dG over T over here with a negative sign out in front, this must be ds for the universe. It's gotta be. So then let's build a sign convention for dG. Now remember, this sign convention that we're gonna talk about that you learned in general chemistry, right? It only matters for situations that are isobaric and isothermal. So we have ds of the universe equals ds of the surroundings plus ds for the system. And we can see that now based off the arguments that we've made. So we know for a spontaneous process, this is positive. So what does dg have to be for a spontaneous process? If dg is negative, then I'll cancel this negative out in front. It's mapping on to ds of the universe to make this positive. Oh, this is negative, a negative cancel to give me a positive. dg, or delta g, is going to be negative for a spontaneous process. We know that ds of the universe, right, can be 0 for a process at equilibrium. And so for a process at equilibrium, when G maps onto the second law for an isobaric isothermal process, the only way to get 0 on the left-hand side is for dg to be 0. Then we're at equilibrium. Right? And finally, building up our sign convention, we know that if we get a ds of the universe that's negative, it doesn't really mean that it won't happen. It means that the reverse process will happen. It means that the reverse process is actually giving us a ds universe that is positive. So then how do I get a negative here? Well, dg has to be positive, right? Because a positive and a negative will give you a negative value. So when we get a positive dg, all right, positive delta g, the reverse is spontaneous. So again, it's of critical importance to kind of realize the reason that you learned about G is because of this mapping that occurred, all right? dg is equivalent to or relates directly to dsu, or delta S of U, the change in entropy of the universe under certain important common situations for us. So the sign convention that we learned in general chemistry, it really only applies under certain conditions, but again, it's really important to know. And I know I said it before, but one last time, there's no way around the second law. The reason that these thermodynamic functions give us a sign convention for spontaneity is only because under certain conditions, they look like or map onto the second law.